Hello everybody, in this video I'm going to talk about our recent WACV2026 paper, Decomposition Sampling for Efficient Region Annotations in Active Learning. The goal of this paper is to reduce annotation costs for dense prediction tasks such as semantic segmentation and object detection. One way to do this is active learning. In active learning, we select the most informative samples for annotation instead of passively annotating everything. We can still maintain a performance that is comparable to a model that is trained on the fully annotated data. And actually, we achieve this by frequently updating the model to actively guide the selection of annotation samples. For example, those that the current model is most uncertain with, or a set of samples that diversely distributed across the feature space. In dense prediction tasks such as segmentation, region-based active learning has been shown to be more efficient than image selection. As I said before, the annotation selection is always based on the prediction of the previous trained model. Here, as we can see, the estimated segmentation. Based on the segmentation, we can calculate the informativeness of all region candidates and select the most informative ones for annotation instead of annotating the entire image. On the right-hand side, we can see that the region selection is always more efficient than the entire image selection, which is represented by the dots. And this is true across all three annotation selection strategies. In this paper, we focus on diversity-based region selection. The standard pipeline starts with image partition, followed by feature extraction for all region candidates. And after performing clustering on these features, we select the class center as a representative annotation set. However, this standard method has limitations. The extensive feature calculation for all regions and the following storage make it very difficult to scale to large dataset or large-sized images, such as the gigapixel-sized histopathology images and 3D images like CT and MRI. And the representative region selection can also lead to task-irrelevant sample selection, such as those from clusters that represent image artifacts. And more importantly, the method selects annotation samples without considering the current model weakness. And this is why it is always necessary to complement diversity sampling with an uncertainty sampling method. In this paper, we propose decomposition sampling, a new diversity-based region selection method that addresses all previously mentioned limitations. We started with decomposing the image into class components based on the segmentation predicted by the model trained in the previous active learning cycle, HT-1. This allows us to detect regions for all task-irrelevant classes, especially the uncertain and the minority ones. Image decomposition also allows us to calculate class confidence by calculating the fraction of pixel predictions with high confidence. We use this class confidence to guide the following annotation selection phase by prioritizing the regions from difficult classes. And this removes the reliance to a separate uncertainty sampling method. In the second step, we select the most informative images based on the class confidence weights. This allows us to find images containing diverse class distributions and especially difficult classes. Identifying such images helps to focus annotations on a small set of images instead of spreading annotation regions widely across a large number of images, thus simplifying the annotation process. And finally, we select the annotation regions from the selected images. We first select a class based on the class confidence rates, for example, the pedestrian in this case. Then we take the decomposed segmentation map and identify a region that best represents the sampled class. This allows for a selection of regions from all classes, composing a diverse annotation set. Additionally, our method requires no region feature calculation or storage, maintaining lightweight when applied to large dataset, large-sized images, or tasks with many classes. Our method can also be applied to cases where regions of different sizes are selected without adding additional computation. We evaluated our method decomposition sampling across 3 datasets from different domains, including histopathology, street scene, and CT scans. We can see that our method consistently achieves higher sampling efficiency than state-of-the-art methods by achieving higher model performance given a certain annotation budget. our method significantly reduces the annotation requirements to a very small ratio to achieve 95% of the full annotation performance, which is denoted by the dashed lines. Specifically, by processing only 30% of whole slide images in BRACs, 2.5% annotated area in cityscapes, and 0.12% annotated area in KISS 23. When looking into the results on cityscapes, we find that the high sampling efficiency achieved by decomposition sampling might result from its capacity of detecting minority class samples. Cityscapes is a very imbalanced dataset, as we can see from the figure on the left-hand side. Classes like traffic lights, traffic sign, and rider are significantly underrepresented. Our method effectively identifies regions from these classes across the active learning cycles, and the model achieves higher performance on these classes when adding them into the annotation, leading to in general higher model performance. In summary, we introduced decomposition sampling in this paper. It is a new diversity-based active learning region selection strategy that balances all task-relevant classes in annotation, and especially prioritizes uncertain and minority classes. It effectively addresses limitations of existing standard methods by being lightweight, memory efficient, independent to uncertain sampling, and being easy to deploy and scale. It is also demonstrated to achieve higher sampling efficiency than SOTA methods across multiple domains. Thanks for your attention. For more detailed results and investigations, please refer to our paper.